Dear students, today we are going to see the ionic equilibrium. This is video number 3. In this, the main objective of this particular video class is to understand the principles behind salt hydrolysis, and the second objective is to know about solubility product, and the third one is to summarize the whole lesson, the entire unit number 8. The side heading, first one, salt hydrolysis. So when an acid reacts with a base, we usually get salt and water, and this reaction is known as neutralization reaction. Salts completely dissociate in aqueous solutions to give their constituent ions. These ions produced are hydrated in water. In some cases, cation and anion are both react with water, and this reaction is called salt hydrolysis. So when a cation and an anion are both react with water, and this reaction is known as salt hydrolysis. In this particular lesson, we are going to see 4 types of titrations. The first one is salts of the strong acid and a strong base. So in this particular subheading, we have the examples. Strong base is NaOH and the strong acid is nitric acid. Now we can see the equation. NaOH plus HNO3 gives NaNO3, sodium nitrate, salt, plus water, H2O. This is one reaction. In this reaction, the salt NaNO3 completely dissociates, splits into Na plus and NO3 minus in water. So the equation is NaNO3 gives Na plus and NO3 minus. Water dissociates to small extent only. So H2O, see the equation is equilibrium, both forward and reversible reaction. It gives H plus and OH minus. Since water is neutral, H plus ion concentration is equal to OH minus ion concentration. This NO3 minus ion is the conjugate base of a strong acid HNO3. HNO3 can be splitted into H plus and NO3 minus. So H plus is in acidic form, NO3 is basic form. This is why we call it as conjugate acid and conjugate base. So in this, NO3 acts as conjugate base, and hence it has no tendency to react with H plus. The NO3 from HNO3 is from a strong acid, therefore it does not react with H plus. Similarly, Na plus is the conjugate acid of the strong base NaOH. NaOH, when it splits, it gives Na plus and OH minus. So it has no tendency to react with OH minus. All strong acids and strong bases have no tendency. This we should remember. If it is strong, it has no tendency to react with either H plus or OH minus. This is the basic thing we have to understand from this concept. So finally, it means that there is no hydrolysis takes place. In this case, H plus ion concentration is equal to OH minus ion concentration. Therefore, pH is maintained, and therefore the solution is neutral when a strong acid reacts with a strong base. This is the final conclusion. There is no change in the pH value. pH is maintained. The solution is neutral. Understand? Okay. Now let us go to the second subheading, 8.8.2. Here the hydrolysis of salt of strong base and weak acid. Usually strong base already we have known from the first example, NaOH. Weak acid, usually acetic acid will be taken. Now see the equation. NaOH plus acetic acid CH3COOH gives CH3COONa, this is salt, plus H2O water, sodium acetate plus water. In this solution, sodium acetate is completely dissociated as below. CH3COONa gives CH3COO minus plus Na plus. In this salt, CH3COO is a conjugate base of a weak acid. Acetic acid is a weak acid. So CH3COO is a conjugate base of the weak acid, and it has a tendency to react with H plus. Since it is from a weak acid, it has a tendency to react with H plus to form water to produce unionized acid. Now just see the equation down given. CH3COO minus plus H2O gives acetic acid CH3COOH plus OH minus. So OH is extra now in this case, and therefore OH concentration is greater than H plus ion concentration. So in these cases the solution is always basic due to the hydrolysis, and the pH is greater than 7. Basic means greater than 7, acidic means less than 7. So let us find a relationship between the equilibrium constant of the hydrolysis reaction, the dissociation constant of the acid, which is given as KH is equal to CH3COOH into concentration of OH minus divided by concentration of acetate into water molecule, neutral. It is taken as unity. Therefore the second line, if you see, it becomes a CH3COOH concentration plus OH concentration divided by CH3COO minus concentration alone. The water concentration is neglected because it becomes 1. Next, acid, acetic acid CH3COOH gives CH3COO minus and H plus ion. So for this, if you write down the equilibrium constant Ka, CH3COO minus H ion divided by acetic acid CH3COOH. So if you multiply the two equations number 1 and 2, the first one is 1 and the second one is 2. So multiply these two things. If you see, in the numerator acetic acid is there, in the second equation denominator is having CH3COOH, so these two things will be get cancelled, and one acetate of first and the second equation, that also will get cancelled. So remaining, if you see, KH into Ka is equal to H hydrogen ion concentration and hydroxyl ion concentration. Only these two things will come. But we know that H plus ion concentration into OH minus ion concentration is equal to Kw. So Kw, which we have already seen in the earlier lesson. So from these two equations we conclude that KH into Ka is equal to Kw. KH value in terms of degree of hydrolysis and the concentration of salt, that is C, for the equilibrium can be obtained in the case of Ostwald's dilution law. In case of Ostwald dilution law, we have the equation Ka is equal to alpha square C, but here we have KH is equal to H square C. Instead of alpha square, here we have H square. This is hydrolysis constant. Next, the pH of salt solution in terms of Ka and the concentration of the electrolyte. So pH plus pOH is equal to 14 always. In a solution, The hydrogen ion concentration and the hydroxyl ion concentration both must be equal to 14. So from this equation, pH is equal to 14 minus POH. 14 minus POH is nothing but minus logarithm of hydroxyl ion concentration, OH minus ion concentration. So the minus of minus becomes plus. Therefore 14 plus log hydroxyl ion concentration. Therefore pH is equal to 14 plus log hydroxyl ion concentration according to Ostwald's dilution law. We get KHC square root. Okay. So for square root we have the power of. So pH is equal to 14 plus log KH can be written as KH is equal to KW by KA. So substituting that value we get log KWC divided by KA the whole power of. So if you substitute all these values here, pH is equal to 14 plus, using the power rule, the half of the power will be multiplied before. Therefore half into log KW plus half into log C minus half into log Ka. So using the power rule, the 10 power minus 14, the minus 14 will become the coefficient. Before that we have to multiply. Therefore next equation it becomes pH is equal to 14 minus half log Kw becomes minus 7 plus half log C plus half log pKa. So pH is equal to 7 plus half log pKa plus half log Kc. The next one, hydrolysis of strong acid and weak base. Strong acid is HCl and weak base, here in this case we have ammonium hydroxide. So HCl and ammonium hydroxide reacts and gives ammonium chloride plus water. This is the equation. This ammonium chloride is dissociated into NH4 plus ion and Cl minus ion. This NH4 is a strong conjugate acid of the weak base NH4OH. Ammonium hydroxide is a weak base. So it has the whenever it is weak, it has the tendency to react with OH minus. Therefore the OH minus will be reacted with ammonia. So what is remaining? H plus ion concentration will be there. Now you see the equation, NH4 ion plus water gives NH4OH plus H plus ion. So H plus ions left over. It is not hydrolyzed. Therefore hydrogen ion concentration is more when compared with the hydroxyl ion concentration. Therefore the solution is acidic. Then the pH value will be less than 7. So from this we conclude that KH into KB is equal to KW. Similarly we did for the earlier equation, which is equal to Ka. In this case it is base, therefore it is KH into KB is equal to KW. So KH is equal to, according to Ostwald's dilution law, is equal to H square C. Therefore hydrogen ion concentration is equal to square root of KHC. Hydrogen ion concentration is equal to, instead of KH we can write down as KW by KB into C. So what is pH? pH is minus log of hydrogen ion concentration. pH is minus log of hydrogen ion concentration. So minus log KW by KB C whole power of. So when you split using the product rule and quotient rule, we get minus half log KW minus half log C plus half log KB, because 2 minus comes, therefore it becomes plus of log KB. So after simplifying we get pH is equal to 7 minus half log PKB minus half log C. The next heading is hydrolysis of salt of weak acid and weak base. Both are weak. Example, acetic acid and ammonium hydroxide. So let us consider the equation. Acetic acid and ammonium hydroxide gives ammonium acetate plus water. Ammonium acetate plus water. This equation is not given in the book. Better you understand. So let us consider the hydrolysis of ammonium acetate, that salt. Ammonium acetate gives acetate ion plus ammonia, CH3COO minus and NH4 plus. In this case, both cation NH4 and anion CH3COO minus have the tendency to react with water. Since both are weak, both are ready to react with water. Therefore, what happens? Acetate, when it reacts with water, it gives acetic acid plus OH minus. Ammonia, when react with water, it gives ammonium hydroxide plus H plus ion. So both the equations you have OH minus ion and H plus ion. Therefore, the concentration is equal. The nature of the solution depends upon the strength of the acid or base. Therefore, Ka is greater than Kb, then the solution is acidic. pH is less than 7. Then if Ka is less than Kb, then the solution is basic. pH is equal to less than 7. If Ka is equal to Kb, then the solution is neutral. So the relation between the dissociation constant Ka and Kb and the hydrolysis constant is given by the following expression, which is Ka into Kb into Kh is equal to Kw. So what is the pH of the solution? It can be calculated using the following expression. pH is equal to 7 plus half pKa minus half pKb. The last example, example number 8.8, it is given on sum. You please go through, otherwise we will see in the regular class. It is also very simple. We have to substitute everything in the equation. It's a formula. H is equal to square root of Kw by Ka into C. See, the values are given in the sum. You substitute. The next one, solubility product. We have come across many precipitation reactions in inorganic qualitative analysis. For example, dilute HCl is used to precipitate lead ions as lead chloride PbCl2, which is sparingly soluble in water. At least small amount is only soluble. Kidney stones are developed over a period due to precipitation of calcium. So inside our stomach, sorry, in kidney, the calcium ions, Ca2 plus ions, are depositing as calcium oxalate, which is known as kidney stone. Kidney stone is, in chemical, it is calcium oxalate. Please just note it down. This is an objective type question. To understand the precipitation, let us consider the solubility equilibria and exist for a general equation. Xm yn is equal to mx n plus and ny m minus. The equilibrium constant for the above equation is, that is, a product of the concentration of the product divided by concentration of the reactant. So in this case, K is equal to x n plus power m and y m minus power n divided by xm yn, concentration. So this is what you call equilibria, solubility equilibria. So the constant is known as solubility product, which is represented as Ksp, which is equal to xn plus concentration power m, ym minus concentration power n. The solubility product of the compound is defined as, this is the definition for solubility product, is defined as the product of the molar concentrations of the constituent ions, each rise to the power of its stoichiometric coefficient. That is the number which is used in the equation before, which is known as stoichiometric coefficient in a balanced chemical equilibrium equation. Solubility product finds useful to decide whether the ionic compound gets precipitated or not. Just see the last 3 lines. In generally, we can summarize. Ionic product is greater than KSP, that is a solubility product, precipitation will occur. If ionic product is less than solubility product, no precipitation and the solution is unsaturated. And final one, ionic product which is equal to SP, that is solubility product, equilibrium exists and the solution is saturated. So the last another one example is also given. Indicate, find out whether the lead chloride gets precipitated or not. One example is given. Again the values are substituted. We will do in the regular class. Determination of solubility product from molar solubility. Solubility product can be calculated from the molar solubility, that is maximum number of moles of solute that can be dissolved in 1 liter of the solution. So for a solute XmYn, which is equal to mxn plus and nym minus. From this stoichiometric equation, balanced equation, we get xn plus is equal to ms and ym minus is equal to ns. So KSP is equal to xn plus 1 into ym minus power n. So finally we will be getting KSP is equal to m power m, n power n and s power m plus n. The last example, one relationship is given, barium sulfate and silver chromate. The exercise is also there, please go through. And finally, when we summarize this entire equation, all laws are given. Arrhenius equation. What is an Arrhenius? According to Arrhenius, an acid is a substance and dissociates to give hydrogen ion. According to Lowry and Bronsted, acid is defined as a substance that has a tendency to donate a proton, and therefore the base is a substance which accepts a proton. According to Gilbert N. Lewis, acid is an electron pair acceptor and base is an electron pair donor. And then finally ionic product Kw is equal to H3O plus into OH minus concentration. What is pH? pH is a solution is defined as the negative logarithm of base 10 of the molar concentration of the hydronium ion present in the solution. Simply it can be given in an equation. pH is equal to minus log base 10 hydronium ion H3O plus ion concentration. Then Ostwald's dilution law. When dilution increases, the degree of dissociation of weak electrolyte also increases. This is what dilution law. The next one is common ion effect. What is a common ion effect? When a salt of a weak acid is added to an acid itself, the dissociation of the weak acid is suppressed further, and this is known as common ion effect. And the next, what is a buffer? Buffer is a solution which consists of a mixture of an acid and its conjugate base, or a weak base and its conjugate acid. Buffer capacity and buffer index is defined as the number of gram equivalents of an acid or base added to 1 liter of the buffer solution to change its pH by unity. So an equation is given. Then Henderson-Hasselbalch equation is also given there. Then hydrolysis, we have seen today's class, hydrolysis of strong base versus weak acid, strong base versus a strong acid, and then weak acid versus weak base. For all these things they have given the equation. Now finally, what is the solubility product, for which we have studied the definition also, which is known as the product of the molar concentration of the constituent ions, each rise to the power of its stoichiometric coefficient in a balanced equilibrium equation. This is what solubility product means. So with that, this lesson is over. Dear students, I have given only 3 questions for this assignment. That is solubility product. Define and explain solubility product with suitable examples and determine solubility product from the molar solubility. So with that, this lesson number 8 is also over. Wish you all the best. Thank you very much.